it would be a good time in the class if you've already reviewed the material for the section on the related groups t-test. This places you where you have talked about the z-test, which was in the hypothesis testing chapter, and then there are 3 separate chapters in the book on the one sample t-test, the independent groups t-test, and the related samples t-test. Now is a good time to go back and look at all 4 of these different tests and see what they have in common, see what they have different, and talk about some issues related to reporting these tests in APA format. So I'm going to present, I think it's about 7 questions that are 7 questions at this point in the class that we should be able to answer. So the first question is, what are the equations for each of these 4 techniques? So it would be good for this presentation to pause the lecture at each question, see what you can come up with, and then I'm going to present the answer to each question in the next slide usually. So take a minute and see if you can come up with the 4 different equations for each of these different tests. Each of these tests is going to follow this standard form. The test statistic is equal to a mean difference divided by difference expected by chance. This is what each equation has in common. What each of the t-statistics has in common is that it is a mean difference divided by a difference expected by chance. Now, where the mean difference and the difference expected by chance come from differ across all 4 of these tests. The z-test is not a t-statistic. What separates it from the t-statistics is that the the standard error of the mean is not an estimate. We have the information to calculate the actual standard error of the mean. So the standard error of the mean is the difference expected by chance. The mean difference that we're calculating is a sample mean difference minus a population mean difference. Or excuse me, a sample mean minus a population mean. So we have population information. Now if we're missing some population information, we have to estimate the standard error of the mean. So the one sample t-statistic, we estimate the standard error of the mean. We still have a sample mean minus a population mean. If we don't have the population mean information, we might use a hypothetical population mean, and we can still use a one sample t-statistic. Now, if we don't have a good hypothetical population mean, and we don't have any other information about the population mean or standard deviation, we can still perform tests that are comparing different groups. We can move on to, if we have 2 different groups to compare, we can move on to the t-test for independent groups. We estimate the standard error of the mean a different way using the pooled variance, and this time the mean difference is between 2 sample means. Now it might be that we want to compare the same group to itself on some measure. For example, at time 1 and time 2, we compare the same group. Or maybe we give a group a treatment and measure their reaction to something before and after the treatment. So if we've only got one group, but we want to measure them twice, we can use the related groups t-test. For the related groups t-test, we're calculating the estimated standard error of the mean using the difference scores, and the mean of the difference scores is what's in the numerator. So here are the 4 equations. Okay, so the next question. Why does the denominator differ for each of these formulas? So the denominator for each of these formulas is the difference expected due to chance. With the z-test, we have the actual standard error of the mean. With the t family, we are estimating the standard error of the mean. So we're estimating the standard error of the mean in different ways for each of the t-tests. With the single sample t-test, we're estimating the standard error of the mean based on that one sample. For the independent groups t-test, we estimate the standard error of the mean kind of based on a balance between mean 1 and mean 2, the two different groups. We do that through the pooled variance. For the related groups t-test, our estimated standard error of the mean is based on the different scores that we find. So it's not based on the scores from time 1 or the scores from time 2, for example. It's based on the difference scores, so the difference between time 1 and time 2. We calculate standard error in these 4 different ways. And so I should mention throughout this PowerPoint that the information is presented in the same order every time. So the first equation on this slide is for the z-test, followed by the single sample t, followed by the independent groups t. You'll recognize the pooled variance, which is sp squared. And then the final equation is for the related groups t-test. And I apologize for the formatting error here. S sub d appears twice, but that's just an accident. We can ignore that. And here I have the formula for pooled variance as well. So remember that for the independent groups t-test, when we're calculating that, we had to do an additional step. Before we could calculate the estimated standard error of the mean, we first had to calculate the pooled variance. So it was a little more complicated. Okay, next let's talk about the numerator of each of these equations. How do they differ? Well, I talked about this in the previous slide. For each of them we have a sample mean, and we are finding the difference between that sample mean, the real population mean, or a hypothetical population mean. In the case of the independent groups t-test, it's between two samples. And in the case of the related groups t-test, we find the mean of the different scores, and that is our mean difference. So all 4 of these formulas, we're finding a mean difference. Here's the next question. If these tests are so similar, why would we use different tests? Why can't we use the same test for each circumstance? Well, that leads directly into this question. How do we choose which test to use? So, what information do we need for the z, t, independent groups t, or repeated measures t? Well, to answer that, let's think back on what population information we have for each of the tests. If we have the population mean and standard deviation, then we can use the z-test. If we don't have the population standard deviation, but we do have the actual or hypothetical population mean, then we can go ahead and estimate the standard error of the mean based on our sample, and that's the one sample t-test. Now, if we don't have any information about the population, but we still want to compare groups, we can estimate the standard error of the mean based on those two groups. That's what we do during the independent measures t-test formula. Now, if we want to measure the same group at 2 different times, we can still estimate the standard error of the mean by using the mean difference, or the different scores between those two groups. That's the related measures t-statistic. So it depends on what information we have about the population and what kind of groups that we want to compare. Now, the 5 steps of hypothesis testing, this approach can be utilized using all 4 of these different tests. So the first question about hypothesis testing is, what would the basic null and alternative hypotheses for each test look like? Again, these are in the order of z-test, single sample t, independent groups t, and related measures t. Now, technically, for the related groups, technically, for the independent measures t statistic, the third formula on this slide, you could report the null hypothesis as mu1 is equal to mu2. I will accept either one in this class. Technically, it should be the mean of the first population is equal to the mean of the second population, for reasons that I think were explored in previous lecture. But let's look at the alternative hypotheses now. I should note that the hypotheses on this slide are non-directional. There are directional examples of each of these in the lectures for their specific test. Okay. We need to know, so degrees of freedom was a concept that we first encountered in the chapter on single sample t. We need to know how to calculate degrees of freedom for each test. Now, for the single sample t, there's one group. We take the number of subjects minus 1. For the independent measures t statistic, there are two separate groups. So we can calculate degrees of freedom one of two ways. One is we can take the total number of participants minus 2. The second option we have is to take the number of participants in group 1 minus 1 and add that to the number of participants in the second group minus 1. Now, that's going to turn out to be the equivalent of using n minus 2. Either way works just as well. So I think, that's supposed to be a 1, but it doesn't look like it. We'll pretend that that's a 1. N of group 1 minus 1 plus n of group 2 minus 1 ends up being the same thing as the total n minus 2. Now, for the related measures t statistic, there are two different calculations for degrees of freedom that we need to keep in mind. The first is that if we only have one group of subjects or one group of participants, then we subtract 1 from the total n. But we talked about another design that is used less often, and that is a matched pairs design, or a matched groups design. This is where we have two groups of subjects in the experiment. Now, if there are two groups of subjects, then for the related measures t statistic, we would use the degrees of freedom equal to n, or total n minus 2. So we subtract 1 from the number of participants for each group that we're comparing. Step 3 of the hypothesis testing is computing the test statistic. So I've got here on this slide all 4 of the formulas we're considering. That's what we would be doing for step 3. Step 4 is to make a decision. So if the calculated probability is smaller than the critical probability value, we reject the null hypothesis. Now, you might be thinking at this point, that seems unfamiliar. And that is because we don't usually calculate the probability of achieving a certain t statistic. We instead take a different approach. So calculating the exact probability is a needlessly difficult process for this type of hypothesis testing. Instead, we just look and see if the calculated statistic exceeds the critical value that we find in the back of the book using degrees of freedom. And if the calculated statistic does indeed exceed the critical value, we reject the null hypothesis. This is the approach that we are taking in this class for hand calculations. Using programs like SPSS, we can take the first approach. Now, for the fifth step of hypothesis testing, which is make a conclusion, let's use these example numbers. So this is for an independent groups t-test. Now, what if I were to give you these results from an independent groups t-test and ask you how would we report the results of this t-test in APA format? When we're writing a conclusion about a statistical test in APA format, we need to include enough information that someone that is familiar with statistics could perform the same test and get the same answer. So we need to include information about the type of test performed, the things that are compared, and I have blanks in the equation at the bottom of this page, but the equation that includes the degrees of freedom, the t-statistic, whether the probability is less than or greater than 0.05, and the effect size. So putting all that into its proper notation would look like this, and the top and bottom paragraph are equivalent. Okay, and I guess the top and bottom paragraph are using the same notation, but I meant to say the bottom paragraph is displaying different numbers, just to give an example of a test that found a non-significant result. Next question. What if we wanted to report, so let's go with the numbers we were using from the example before in which the difference was statistically significant. How would you report this result to someone without statistical training? And I have some simple examples here. Just group 1 had a higher mean than group 2. In the case where we did not find a difference, we could say group 1 did not differ from group 2, or did not have a higher mean than group 2. So we've been through the 5 steps of hypothesis testing. Before this talk ends, let's go over identifying the independent variable and the dependent variable. Just a reminder that the independent variable is the variable that is manipulated, while the dependent variable is the variable that is measured. Next question. What is quasi-experiment or quasi-experimental variable? In the case of a quasi-experiment, an experimenter cannot directly manipulate levels of a variable, but still wants to use them to compare groups. So instead of directly manipulating the variable, the experimenter chooses participants based on their level on that variable. For example, if a researcher wanted to compare individuals that own pets to individuals that did not own pets, the best way for a researcher to do this would be to recruit people that are pet owners and recruit people that are not pet owners, and to put them in different categories based on that. So you can see in this example that the experimenter is not directly able to manipulate who is a pet owner, but is able to categorize them based on that, so that would be a quasi-experimental variable. And the last question is, I want to review again, what are the 2 circumstances in which a repeated measures t-test would be used. So, a repeated measures t-test would be used in two circumstances, and you can find that at the bottom of this slide. If measures are given twice, so at time 1 and time 2, the same participants are getting the same measure twice, or if subjects are matched, so a matched pairs design. So it could be the same group getting measures twice, or it could be subjects that are matched to another group of subjects. And the last topic is choosing an independent versus a repeated measures design. So far, the only independent groups design we've talked about is the independent groups t-test. The only repeated measures test we've talked about is the repeated measures t, or related groups t. Well, when we're choosing which one to use, some designs can only be done certain ways. So some independent measures, some independent variables cannot be given to the same participant. For example, there are certain social psychology experiments in which once a participant has received an independent variable manipulation, they then know details of the experiment, so you can't necessarily run them back through the same experiment a second time in the control condition, because there would be crossover effects on the different conditions. So we have to test different participants. So the advantage of an independent groups T is the ease with which it can be used. We can utilize more independent variables because there's no chance of crossover effects. The advantage of the repeated measures T statistic is that it removes individual differences. Okay, that is it for this talk. Thank you for listening.